You got my announcement today, the 11 and 12 extension.
Yep.
So don't have to freak out about that. And we continue with friction. Party of one. Just extreme fatigue.
Yeah.
So we are going to continue with friction. Did you get the handout? Your handout? Yep. We're going to still work on the old one. We got a little delayed on yesterday's lecture, so we didn't get as far as we were supposed to get, but this is, so how we handled some of these problems with crates is that they could slip or maybe they could tip. So you have to make some assumptions, right? So the first problem was we assumed that it was in force equilibrium, so the forces add up to 0. And we checked our assumption, and our assumption was valid. So the force equilibrium held. That means the crate was not going to slide because the resulting value of F that we determined was less than the maximum US times N. And so that confirmed our assumption, but we also had to check that whether the crate could tip. And that was whether, and so for that we assumed we were in moment equilibrium, so that the sum of the moments were all 0. And since the normal force has to shift a little bit to make a counter moment of the applied force P, this distance x is crucial, and you can compute Wx as the counterclockwise moment minus P times 8, having to equal 0. But if that was the case, x would have to be at 2.5. So x would have had to gone out here. So the normal force would have had to be applied off of the crate, which is not possible. So the crate would tip. And with a little extra work, you can say, well, what force, with a little extra work, you can figure out what the force was to make it tip. By setting x equal to 2 feet, you can solve for P that makes the moment equal 0. And that would be the minimum force required to tip the crate. But we just plugged in an x of 2 feet into the sum of the moments, and we found that these were not 0. Again, you get a net clockwise moment, meaning that that thing's going to be tipping. So that takes us to this notion of impending motion. So those first two questions were like, is this thing going to be stationary? Is it going to slip, or is it going to tip under these circumstances? The other kind of questions we get asked with friction is, what is the minimum force to get this thing to start slipping? And or to prevent it from slipping. So here's the question: is what's the minimum force P to prevent the 200-pound crate from sliding down the 30-degree incline if the coefficient of static friction is 0.25? And again, with these kind of problems, these impending motion problems, we use the equilibrium equations. But if you're at impending motion, what do we know? We're at impending motion. What do we know? Something might move. Yep. We know that friction is what? When you're at impending motion, when the thing's about to move, what do you know about the friction force? Yeah, impending motion means you're actually not moving yet. But if things change a little bit more, then you're going to move. So at that point, we know that, so we use the equilibrium equations. And the notion that Fs is at its maximum value, right? So yesterday we were just seeing if the, if the friction force was less than that, meaning it would hold. But now we can assume at impending motion, so with these impending motion problems, we're assuming that the friction is at its maximum value. And that again helps us reduce the number of unknowns, because with friction, you just have these extra unknowns because that extra force in there, right? And so here's the problem, and I'm trying to figure out how to change the color of my pen on this thing because I'm not doing it with presenter mode. Let me see. Why isn't it here? Review. I guess black is okay, huh? I've ordered Office 2013, so it'll be here next week, off of eBay. That's the only place I could find it. You can get all these like free downloads, but I can't trust that. You know they're going to get some crazy virus if you do that. I thought I was able to change the color of this thing before, though. Why can't I not find that color change? Is that what you used last year for all the lectures? I used it last fall, and then in the spring I went over to my Surface, and I started noticing those jerky things all last spring, but I just figured it was me and just kind of ignored it. And it didn't seem like it was as bad until I adopted this machine, figuring I would finally get over it. Oh, here's draw, there we go. And here is a red pen. So we draw the free body diagram again, and here we're actually, the thing's about to slide down. We just want to keep this thing from sliding down, right? And so the normal force is this way. The question is, and the weight of the body is going to be like this, going straight down, right? And the question is, which direction is the friction force going? It's pointing down the plane. Pointing down the plane, right? It always opposes the force of your plane. No, it's not. Which direction is impending motion? What this impending motion is, the crate's about to slide down the plane. Which direction is impending motion? Impending means it's about to slide. We're trying to keep it from sliding down the plane. So impending motion is what? So put that on your sheet. Well, there's P. We're pushing up on that crate. But we're only pushing, we're not trying to make the crate go up. We're trying to keep the crate from going down. So the friction always, always, always opposes the direction of impending motion. If the thing wants to go one way, the friction is going to oppose that, right? So when you figure out what impending motion direction is, then friction is going to go the opposite of that. It's going to go up. So we draw the friction going up. In this case, friction is helping us because we don't have to push as hard. If it was on a frictionless surface, we'd have to push a lot harder to keep the thing from falling, right? But we're using friction to help us. And with this W force, we can resolve it again into a tilted axis where we have the X and the WX and the WY directions. Again, our axis is tilted this way, like so. Here's X, here's Y. This angle is theta here. Okay, and so the sum of the Fy's, okay, that's 0. So that's going to equal the normal force, right, minus W sub y, the y component of W. Again, we're tilting our heads so that the y-axis is sort of skewed to the angle like that, which makes it easier, a little bit easier to do the analysis. It's kind of more convenient to do it that way because the friction force lies along that x direction then, and the normal force is perpendicular to that. You could do it without tilting the axes, but then you have a lot more trig in your equations. And so that equals n minus 200 times the cosine of 30 degrees. I don't have enough room there, so I'm going to do another line. So that equals n minus 200 cosine of 30. Oh, so therefore, n equals 173 pounds. Okay, we sum the fx's. Oops, that should be x. And we have p in the positive x direction, we have f in the positive x direction, and we have minus wx in the negative x direction, right? The x component of w angling back down that plane. And at the limit of friction, F equals mu Sn, which equals 0.25 times 173. I didn't leave enough room for again. So that equals this is a mu. Okay, so we can solve, we can basically say that that means that P is going to equal Wx, which is 200 pounds times the sine of 30 degrees, minus 0.25 times 173. And it turns out that P is going to equal 56.7. Okay, P is 56.7 pounds. What happens if P is 56.5 pounds? It starts sliding down the slope, right? So that's a 200-pound crate, and we're able to keep it from sliding down with only 56 pounds of force, which is pretty good because friction is supplying a lot of that force. It's supplying a quarter of 173 pounds, which is, what's that, 40 pounds of force? Friction's providing 40 pounds of force, assisting us to keep that crate from sliding down. Friction's our friend. What if we apply 56.8 pounds? What do you think, 70? We apply 56.8 pounds, is it going to start moving? Because now we're start moving up. What do you say, Matthew?
I feel like it's
not going to move up, right?
Yeah. The force from the weight of the crate is 100, right?
Yeah, so remember, so friction force, you know, so when we're at the limit of static friction, if we lowered our force a little bit, it's going to slide down. That means we go into this domain. But if we increase our force, then the friction just becomes smaller. but the object is still stationary until we push it hard enough that the friction force has to start opposing us now, right? Because we want this thing to go up the crate. Friction's going to stop us from pushing it up the crate too. We're going to push extra hard to get that thing to go up the crate to combat the force of friction. Right? Because friction is one of these things. Friction is what's trying to keep things stationary until you exceed the limit, then it can actually start slipping. But if you're within the limit, then the object is not moving. And what we've done is by pushing a little bit harder, we're just keeping the friction force within the limit, right? So we can put a note here that says, note, larger P will result in a smaller F. Smaller F meaning it's within its limit, meaning it's not moving. It'll be still stationary. You can read that. That says stationary. Yeah.
So when, like you said, when we exceed the limit of the static friction, like on the graph, we go further to the,
yep.
when our force is greater than that.
Yep.
When you say that the frictional force it's still the same, right? Or is it decreasing?
It gets smaller. Once you start moving, the friction force gets smaller. It's the kinetic friction is less than the static friction. Yeah. Limit, yeah. And so then the question is, which is a great question to ask, same situation. What minimum force P is needed to start the 200-pound crate sliding up the 30-degree incline? Okay, because 56.8 is not going to actually get it moving yet. How much do we have to apply to get that thing to move, right? These are all really interesting questions. So now, you know, we have the same free body diagram, but the impending motion is up. Now friction is fighting against us. Makes our job harder. We've got the normal force and friction now pointing downhill. Your back is feeling more sore just thinking about it, right? Pushing that thing up that hill is going to be really painful. It's 200 pounds. You've got that W of 200 pounds, and that, of course, resolves into a WY and a WX. And our axes are, again, tilted like so. So the sum of the FYs equals 0 again. So it's N minus WY, and that's the same. Basically, it's N minus 200 times the cosine of 30. So once again, N, the normal force hasn't changed. It's still 173 pounds. But now our equation for the X components is a little bit different because the friction force is pointing in the opposite direction. It's pointing in the minus direction. So that's P minus F minus W sub X. And again, impending motion means we're at the limit of the friction force. The friction force is at its limit at US times 10. And again, that's 43.3 pounds that we're getting of, in this case, resistance we have to overcome. So, so P is going to equal 200 times the sine of 30 plus 43.3. And that means it's going to equal 143 pounds. 143 pounds to push that thing up. Does that make sense?
So what is the F equal the 43.3 represent? Is that the fact that the force that needs to be stationary, or what's that maximum force of the stationary?
What that 43.3 represents is the maximum force that friction can apply in that system. Can't go any bigger than that. If the friction force needs to be bigger to maintain equilibrium, it can't, and so it will start moving. Yeah. So in this situation, if we're pushing at 142 pounds, what's going to happen? No, we're not pushing enough to get it to move yet, because the friction force is just going to be a little bit smaller. The friction force can go as high. So we got, like, if it was on ice, right? If there was no friction at that interface, it would take us 200 sine of 30. This would be the force with no friction. To keep that thing from sliding down or up, right? It's the same in this problem, right? So in other words, if there was no friction and you just wanted to hold that box steady, you would have to apply 100 pounds of force pushing up on that thing, because the 30-degree angle is taking some of that load, right? The normal force is taking a lot of that load, half of it, and we're taking the other half to keep that thing from sliding. That 200-pound force. We're able to hold that force steady on a frictionless surface with 100 pounds of force. If there is friction, though, and so if there's no friction, we go a little bit lower than 100 pounds, it starts sliding down. We go a little bit higher than 100 pounds, it starts sliding up, right? There's no friction, right? It's either going to be stationary or, yeah, right? But if there is friction, see, then that gives us a little more room for keeping that thing stationary, right? Because the friction starts to help us, right? So, so this number is 43.3 pounds here. And when we're trying to keep the thing from sliding down, if we're pushing it like 95 pounds, right? Well, the friction only needs to provide 5 pounds to keep that thing from moving, and it can do that easily, right? So if we're pushing 95 pounds, it's still not moving. If we push it 80 pounds, is it moving? Because friction's gonna still help us, right? It's gonna keep that thing from moving until we require 43 pounds of friction to keep that thing stationary. And at that point, it starts to move. If we go lower than that, if we need more than 43 pounds, it actually starts to move down. I don't think I'm explaining this well enough. We need to do a lab on friction, darn it. This would be a really good lab. Sorry? Yeah, we should do a lab on friction. Maybe we should just make one. Maybe we should just do one next week. It'd be really easy to just do one all together. Yeah, carpet, table. We could just do something pretty easily, yeah. I've got a little postage scale for force. We could push, like a spring scale. We could do an experiment just like this with, like, say, a box of Kleenex on a tilted table, and we could estimate the coefficient of static friction. We can do all that stuff. You want to do that? Kind of fun. Maybe next week. More real, right? All right. Anyway, in this one thing, the only difference between these two problems, right, is the direction of F. And if you were going to plot this, let me just insert a slide here. What this is saying is, let's see. So So we found basically that, to kind of summarize these things, the same crate, right? And this is the kind of thing we could probably do in the lab, right? So it says we have to provide 56 pounds to keep it from sliding. So if we sort of draw like P here, and not sure what we could draw here. We could draw F, and actually this would be kind of interesting, right? Because when P is 56.7 pounds, what was friction force? It was at the limit, say 43.3, right? So right here is 43.3, right? There's the friction force. And if we're in this region here, so below this region here, what's happening to the crate? Sliding down, right? Right? And as we increase this thing, when we get to 143 pounds, what's the friction force again? Well, it's actually, the sign is flipped. So I don't know if I should do a sign flip or just talk about the magnitude of the friction force. Let's just talk about the magnitude of the friction force because the direction is flipping, right? It's basically at 43.3 again. And if we go into this region, what's happening to the box? It's moving up the plane, right? Slides up, slides, or it slides up the plane, right? And in this region right here is where the crate is stationary, right? So our applied P ranging from 56.7 to 143, nothing actually moves. It's static in that region. And the force is actually dropping. The magnitude of the force is dropping to 0, right? So there's a point here where, you know, no friction force is required, right? That's like midway through, that's like at 100, right? That's like the same thing as if you were on a frictionless surface. At 100 pounds, you could hold that thing stationary even if there was no friction, because you don't need any friction force to keep that stationary. But then the sign flips and it starts growing again until it reaches its maximum in the other direction, right? So here is, you know, F is points up, and here F points down. So I could sort of keep it going down like that if you want to think of it that way, right? The sign, the direction of F actually changes, right? And you know, that's what, it's pretty easy to show you. Even just this, you could take anything like this eraser on top of the manila folder, right? I can find, you know, here I have this box of Kleenex. There's an eraser on a box of Kleenex. I can tilt it to the point where it starts to slide, right? I can go beyond there and just figure out, okay, well, how much, okay, I need to hold it, right, with a certain amount of force. And there's not a whole lot of range. Friction force isn't really significant enough. But with a proper surface of friction, you can tell that there's a force to get it to move or force to keep it from moving. And those are two different forces. Question?
The slope line is going down
Uh-huh.
from 43 to 100.
Yeah. That's the size of the friction, the magnitude of the friction force. That's this, on the y-axis, we're plotting the magnitude of F.
Or then it'll change directions at 100.
Yeah, because if there was no friction force, right, in order for this thing to be in equilibrium, P would have to equal W sub x, which is 200 sine of 30, which is 100 pounds, right? Yeah, it's a kind of a cool thing to conceptualize it, right? If you don't have this, then you're just plunking equations and it doesn't really make any sense. But this is one of those concepts that can really help you understand what's going on with friction. So yeah, we should do a demo of this thing next week. Okay. The other thing we can look at is some systems have multiple points of contact with different coefficients of friction. And if you ever find yourself painting houses for the summer, you might think about, what can happen to cause your ladder to slip. And here the question is, what is the maximum angle? I think what they're saying is this should actually, sometimes even the questions are actually worded wrong. These are really easy questions to kind of confuse. It's actually the minimum angle. The minimum angle for stability. The maximum angle for stability would be 90 degrees, right? If they go past 90 degrees, if they're talking about this angle right here, right? If that angle goes past 90 degrees, you're going to start falling backwards the other way. That's something that we're not, we don't need friction to help us with that. But if the angle is, if angle theta is less than 90 degrees, you can agree, right? If the ladder is something like that and you try to stand on it, it's going to slip down, right? It's not going to be able to hold you, right? So there's some minimum angle theta that you need to keep the ladder from slipping based on the coefficients of friction at those surfaces. Right? And so we can use these same techniques, right? So when the ladder moves, it slips at two surfaces. It slips at A and B. And at the limit, the friction force at A is going to equal its maximum value, which is going to be what? Yep, times the normal force at A, right? And FB is going to do the same thing. It's going to be 0.2 times the normal force at B. Okay, well, we got to draw these things, right? We should have done that first, but let's add those forces. So we know that the weight of the painter is going to be applied at its center of gravity, W. We've got a normal force here at A pushing up the ladder. And impending motion, which way is impending motion? At A. Yeah, the thing's going to start sliding to the right, right? So the friction force has to oppose that, so the friction force is going to be going to the left. You're going to have a normal force at B, keeping the ladder from tumbling into the wall. And impending motion at B is what? Down, so the friction force at B is going to be pointing up. Now there's some additional trig that we need to determine. For instance, what is the height of point B? What is the height at point B? A 10-foot long ladder, angle of theta. Yeah, 10 sine of theta, right? And what's the distance to point A from the base? Sounds good to me, right? 10 cosine of theta. It's a triangle. Okay, so again, with our equilibrium equations, we can say, well, so the nice thing is, so by assuming that we're at impending motion, we know those friction forces are 0.3 NA and 0.2 NB. They're not unknown. Like in this problem, for to be stationary, the friction force could be anywhere in this range, right? But when we are at impending motion, it pins us down to either this point or this point. So there's no, there's one fewer unknowns there, right? That's how impending motions can be solved. So the sum of the Fx equals 0 is going to be, now we've got our diagram set up, it's going to be NB minus Fa. But we know Fa equals 0.3 Na, so therefore we can determine then that NB equals Fa, and Fa equals 0.3 Na. So NB equals 0.3 times Na. The sum of the Fy's equals 0 is going to be, well, you're going to have an Na going up. You're going to have an Fb going up. And you're going to have a W going down. And Fb we know is 0.2 NB. Because you're at impending motion. So Na plus 0.2 NB minus W is the sum of the Y forces. But if NB, so FB is 0.2 NB, and NB is, as we determined, NB is 0.3 NA, we can sort of reduce our unknowns here and say, well, okay, so that equals NA plus 0.2 of NB, but NB is 0.3 times NA, right? So that reduces the NA out of it, the NB out of the equation, which is nice. Minus W, and that means that W equals 1.06 NA. Which is kind of interesting. It doesn't depend on the angle. It sort of means NA is going to be 94%, reciprocal of 1.06, 94% of the weight of the painter. It's taking 94% of the load. The friction force of B is taking the other 4% of the load. Well, the last equation we can use to basically figure out what theta is. So we still have, this equation W equals 1.06 NA is not going to help us find theta yet, but it does help us reduce unknowns here. So if we have a W, we can place it with an NA. We can place, or replace NA with a W. And the last thing we're going to do then is the sum of the moments. So we can take the sum of the moments anywhere, but we can choose to do them at B. And this is going to equal, well, what are the moments at B? Giving us a moment at B. Fa, right, times 10 sine theta, right? And is that negative or positive? Okay. Right, so this force here is giving you a moment about B. This is the force, that's the moment arm. And there's another moment, another force giving us a moment. 70, do you see another moment? Yeah, NA times 10 cosine, positive or negative. And what else? Anything else giving us a moment about B? Or W, right? W times, and they're telling us the moment arm is 3, right? W times 3. But FA is 0.3 times NA, which is nice, and W is 1.06 times NA. So we actually have this way we can now write everything out here. We can say, all right, so 0 equals minus 0.3 times NA, because that's FA, right? FA is 0.3 times NA. We figured that out already because of impending motion. And that's going to be multiplied by 10 sine of theta. Plus NA times 10 cosine of theta. Can you read that? I'm kind of writing small. Is that readable? And then minus, but we know that W is 1.06 NA. So 1.06 times 3 is going to be 3.18 times NA. Is that cool? So we worked out and got rid of the W. So then we have this, it's not an easy equation to solve. It's, I think it's called a transcendental equation. But if you cancel out all the NAs, which you can by dividing by NA, you're going to get that 10 cosine of theta minus 3 sine of theta equals 3.18. And you can solve that using a computer or, with guessing and checking. You can just try a range of angles and kind of get closer and closer to where you find the value of theta that makes that equal to 0. You can't really solve that using any trig formulas that I know of. But the answer when you do that is that theta is going to have to be 55.6 degrees. So the ladder has to be set to at least 55.6 degrees or higher. Otherwise, the ladder will slip. Yeah. Yeah, I like these problems. They're very practical, right? They really tell you whether someone's going to have a problem or not. And it doesn't even matter how much they weigh. Yeah, if it's a boy standing on it or a very large man or a grizzly bear, it's going to be the same angle. So the next section is going to be impending motion at some points. Maybe we should just hold that off until Monday. How are you guys feeling? Or, maybe we should do some, is it on the handout? Is there a third handout? Why don't we do, well, we have 5 minutes. Why don't we sketch out, and you can just do this real fast. I didn't make a handout for the in-class problems, but I can show one real fast so you can try practice solving one. This is assignment 13, I think, right? Is it 12? It's 12. Oh, yeah. Okay, this one's easy to sketch out, right? You can just draw this in your notes somewhere. The minimum force to prevent the 30 kilogram rod from sliding. The contact surface at B is smooth. That means there's no friction at B, which makes it a little simpler. And the coefficient of static friction between the rod and the wall is 0.2. So I'm going to take a picture of this real fast. And the answer is supposed to be 155 newtons. So there's a 30 kilogram rod. So how are you going to do the free body diagram? That's probably all we have time for. 3 minutes too. So why don't you try drawing the free body diagram and I'll see if you got it right. So what'd you get? What force is around there? Nothing? A force. Just give me one force. The weight force, which is where? Yeah, so we're gonna have a weight force pushing down, and the weight is going to be how much? $294. Okay, so that means another force. Okay, at where? On the bottom at B. Well, but it says here the contact surface at B is smooth. So there's no friction force there. Yeah. So how about another force? Sorry? Well, that's already drawn. I mean, force P? Yeah, force P is already drawn here. How about another force? Okay, where? At where? At B, right? So we have a normal force at B. No friction force because it's smooth. All right, Matthew, another force? Okay, going which way? Going up? Yeah, so which way is impending motion? If we're preventing the rod from sliding, what's the direction of impending motion, 70? Well, just if the rod's going to slide, we're trying to the minimum force to prevent it from sliding. Which way is it going to slide? Down at A, right? Or left at B, right? So the friction force has to be going in the opposite direction of that. So if it's going to slide down, so here's impending motion at A. That means the friction force at A is going to be going up. And what other force at A is there? Normal force at A. Yeah, that's the start, right? And you can kind of see how, you can start writing the equations now. You're at impending motion. And at impending motion, what does that mean about FA? which is what? What's the max? Yeah, so FA can be changed to 0.2 times NA. Yeah.
Does that mean we assume that the maximum friction force, we're gonna have to use that, which is the normal times 0.2?
Yeah, the minimum force needed to keep it from sliding is going to require the maximum friction force at that interface, helping you, pushing you up. If it had said, what's the minimum force P to make the rod slide up the wall, you know, then that's another problem.
So you still use the max friction force, right?
Yeah, except now the arrow's pointing the other direction.
Yeah.
Mm-hmm. And it may be, there is this thing called self-locking, which I didn't talk about, but like if the rod is like this, and no matter how hard you push, you can kind of tell yourself it's not going to go up the wall, right? It's called self-locking. Because if you keep pushing harder, you're just going to increase the normal force, which increases the maximum friction force even more, right? But when you, so I don't know if that's 45 degrees. It might depend on how much friction there is. But you know, if it's like this and you push on it, you can convince yourself you can make it go up. But I think in this case, yeah, if it's less than 45 degrees, I think you're going to just, it's sort of not, it's never going to go up. That would be another interesting question to ask. Yeah, we really should have a lab on friction. That's one of these things. It's conceptually, it's really sort of kind of a little perplexing until you actually play around with stuff. Yeah, maybe not a lab, but like a demonstration. Well, the coefficient is the it's the wait, what is it again? The coefficient of friction. I forget which one's the angle is the arctangent. So coefficient of friction is the tangent of an angle. That's a great question. Let's go back and look at the oops, wrong slide. Let's look at the definition here. So this angle, right? So phi s, and that means the tangent of the angle is mu s, right? And that would require basically, I don't think it is ever going to be, that would require Fs to be bigger than a normal force. Why doesn't that seem possible? I don't know. Well, it could. You know what? I mean, really, let me see. I mean, what's the tangent of 1? That's 45 degrees, right? The arctangent of 1 is 45 degrees. So if somehow the thing could stay adhering to this thing at an angle greater than 45 degrees, then that would have a higher than 1 static coefficient of friction. So Velcro, you know, if you hold something with Velcro, that could certainly hold it at a 45 or even higher. It could hold it at 90 degrees. That's a static friction coefficient of affinity, depending on how heavy the object is. But that's not really friction. I think that's something else. Try. Can we ever get, so you did a lab in 3A then where you played around with this? I think, look at, that's holding way past 45 degrees. Wow, that's really hard. No. No, it's just, it's got a lot of ink on it. Well, this is a perfect one to try do a demo with. I'll do that next week. Oh. Dry erase, but it has a lot of gook on it. It's really gross. Or we should just barge into the physics lab and demand a demonstration of friction. You're not teaching us important stuff. All right, I gotta run.